comment from me. For the journalists who may be here, you may have noticed that we've been discussing about the collapse of civilization, the end of the world, but as you know, these are just theories, just like peak oil, so there is nothing to worry about. The next speaker is Salvador Pueyo, again, models.
Well, Carlos arrived very far in the last speech. Now my intention is to begin again from the beginning. Well, this is how everything began, and the ultimate reason why we are here. Well, as you know well, Haber made this forecast for the conterminous U.S. oil production, which was not exact, but was really good. In fact, it's the best ever done, probably. And well, Haber had the idea that oil, after it began to be produced, after this they could pass by several peaks. In fact, many different things could happen, but eventually it had to decline for physical reasons. But besides this idea, he made some generic forecast for physical reasons, but he also tried to use a specific equation to model this curve of oil depletion. And, okay, which is just a basic model, which he didn't pretend it to be universal, but is useful, and it has been widely used also for other forecasts, which was the logistic equation. Okay, this has, well, as I said, is widely used by the peak oil community, but it has also raised some criticism, considering, well, why such a, first, how can you justify this specific equation? Then there is the problem that it's a rigid equation. How can you introduce economic factors, political factors, the kind of feedbacks that Carlos was commenting, for example? And, well, my intention here is to discuss a little bit the specific shape of this curve. Well, some people say that, in fact, the specific shape is not so important, but I think that there are some equations that do a little better than others and that make it easier to introduce also other factors, because they have perhaps a clearer physical meaning. No? So I'm going to introduce some suggestions of how we could first justify why this equation works well, and how could we even modify it a little bit and to try to improve it a little bit. No? So, well, in fact, I'm not a specialist in oil. I am a theoretical ecologist. But Haber took his equation, the logistic equation that he used was an equation initially proposed in the field of demography, and in fact is one of the keystones of population ecology. So this is why I felt inspired to do something also with this equation. In the case of population ecology, as for example in this instance with yeast, with a culture of yeast, the logistic equation is like the one that you have right in there, and here is the abundance of yeast, the number of cells of yeast in this case. What this equation is telling us is that at the beginning, when you introduce the first few cells of yeast, they are gonna grow exponentially. Here you have the R parameter, that means exponential, that introduced the exponential growth. But at some point, there will be less room for this yeast. We are considering here that there is a permanent supply of nutrients, but it cannot sustain an infinite population of yeast, of course. So at some point, it should begin to slow down until reaching a steady state population that is fitted to the supply that is receiving, that, as I said, is a permanent supply. Okay, as you see, in the case of yeast, works pretty well. In other cases, it doesn't work so well. But it's a model for essentially for a sustainable situation, for a permanent supply of a resource that is used sustainably by some population of some organisms, in this case by yeast. However, we are dealing with quite a different situation, which is an unsustainable use of a non-renewable resource by another kind of organisms that are ourselves. And the way Haber the way that Haber figured out to use this equation for such a different situation was just to take N, in this case abundance, not as an analogous of oil production or as the volume of oil industry, But he introduced here the cumulative production, so all of the production that has been done in the past. And of course, when you run out of oil, it cannot increase anymore. Of course, it cannot decrease because it's just the past. It's just the cumulative production, so it reaches also a steady state. Well, but indeed, this works quite well. I mean, it was an interesting way to proceed. It gives an approximate fit. But you can see also that it is a little artificial. And in fact, there are other alternatives, because thinking in terms of what ecology can offer, because, well, this was a model, as I said, for a sustainable use of resources, but there are also biological instances of completely unsustainable use of resources, and there are models for some of them. Well, yes, this is what Hubbard did, to use the cumulative production, which is Q, to model the increasing cumulative production, which is, of course, production, P. But, well, I was saying that there are instances of unsustainable growth. For example, this is a nice one in our context. This is a bacterian culture for which you only introduce the first stock of nutrients, and you introduce no more nutrients, and this is their energy consumption. This is taken from the PhD thesis from Jorge Wagensberg. And as you can see, this bacterial culture underwent 2 Hubbard cycles. So they first depleted the easy-to-use resource. Then they had some decline because they needed some time to develop the metabolic pathways to use different resources, which is the equivalent of the time to develop different technologies. And, well, and it seems right now that we are not behaving with more intelligence than this bacteria, or with more foresight. Okay, there are also other, this is in a lab, but there are also well-known instances in nature. In nature, there are many instances of periods of relative stability, and then outbreaks of pests like locusts, for example, in which there is an effusion of energy that is necessarily ephemeral. No? After some time, well, they first grow very fast. They eat the resources much faster than they can regenerate, and then they collapse. This is something that happens in pests. But the best studied instance is the instance of epidemics. In the case of epidemics, we are the resource, we or other species. And also you have some organisms, either bacteria or virus, that first grow very fast, much faster than the resource can regenerate, much faster than we reproduce. And at some point, they run out of resource. I mean, well, they don't completely run out, but the density of susceptible people gets quite low, because many people either is dead, as in plague, or is immunized. So at some point, there is so many dead or immunized people that bacteria or viruses cannot keep the same rate of growth, and they collapse. So they also have their peak here. And okay, I think that many environmentalists have compared sometime oil industry, or even the industrial society as a whole, with a pest, if not an epidemic, at least a pest. But few would imagine that the questions that they use for epidemics can also be useful for the field in which we are working in this moment. Okay, so now I'm going to introduce a very simple equation of epidemics to see if it can shed some light on the issue of peak oil. The simplest equation that is used, but that is very widely used, is the SIR model, which classifies the population of hosts, like humans, for example, in 3 groups, which are susceptible people, infected people, and removed people, which comprises people who are either dead or immunized because of the epidemics. Okay, if we want to make a comparison with the case of oil, one possible way to proceed would be to compare susceptible people with oil deposits or oil fields that are still intact, to compare infected people with oil fields that are producing, and removed people with exhaust oil fields. The problem with this approach is, well, okay, it's very illustrative, but of course the size of fields are much more diverse than the size of human bodies, so perhaps it's more useful not to think in terms of fields, but to think in terms of amounts of oil, so you could distinguish the oil that is still underground, the oil that is in the process of being produced right now, and the oil that has already been produced. And of course, the category of oil that is in the process of being produced is not very well defined. But just, if we just consider that is quite small as compared to the sum of the other categories, you have enough not only to apply the model, but also to simplify the model even more, even though it's already quite simple. Okay, the model is this one. We are not going to enter into the details. Just notice that it is a very simple model, as simple as it can be. I should say that there is also already a precedent of using this model. GIMC in the oil drum introduced also this model without making the epidemiological connection, but he didn't develop it, so all the rest that comes after here has not been done. He just made some simulations. Okay, as I said, we can simplify this model, assuming that the infectious, the oil that is in the process of being produced is small. And if you simplify this model, you get this, something that looks quite similar to the logistic equation, but is different. So in this case, you have the production that is, not the cumulative production, but production that is increasing exponentially, with the notion that, okay, you are producing, you are investing part of what you get in more production, so it increases exponentially. But also you have an effect of scarcity. We don't know, usually we don't know how much oil is left, but we can measure it indirectly in terms of how much oil has been produced. So there is an effect of scarcity measured through the oil that has been produced, Q. And at some point, at QP, which means peak, you get maximum, and then this equation becomes negative, so production begins to decline. An interesting point is that if you solve this equation and extract the expression for production, you get this, which now I'm going to highlight one part. If you take only this part that is highlighted in purple, this is the logistic equation. And the rest of you have is a new parameter that was not there, and this is a parameter for the initial conditions. The initial conditions, I mean the situation, of course, before you have this exponential growth in which the oil industry feeds itself, at some point you need an initial investment, and this is what defines these initial conditions. And okay, so interestingly, the logistic equation used by Hubbard is a particular case of this one, in which phi, the parameter of the initial conditions, is 0. But you can define a more general situation, and in fact you can argue that usually phi should be positive. Well, the upper equation has already appeared too in discussions in the oil drum by Kebab, but only technically as a derivative of the logistic equation. Here I'm introducing it as a different model that leads to a generalization of, in fact, a small modification of the logistic equation. So, if this equation works, now we are gonna study this. If this equation works, it will tell us some interesting stuff. First, it can justify, starting from a more mechanistic standpoint, it can justify why the logistic works quite well, because once you reach high levels of cumulative production, phi is not so important, so that the logistic can also give a good fit. It also justifies while at the beginning, while the cumulative production is small, you can expect larger productions, which is something that happens in practice. Another interesting point is that this phi, as I said, is just a parameter of initial conditions, so that if you have a strong economic fluctuation and then the curve gets disturbed, even though later you keep the same structural parameters, the same reproduction, well, the same R, the same QP, just because of this fluctuation, the curve will can have a permanent change because the initial conditions will have changed. And another interesting point is that you can, since we extracted this from an epidemic model, you can give a more precise physical meaning to these parameters, which I will explain later. So it is easier to introduce economic predictors also in how these parameters could change. So, but, well, before doing that, I will first test this model with a very simple case, which is the case of Norway, which is interesting because you have good data, it has already peaked, and overall that the curve is simple. There is no evidence of a strong economic or political disturbance. Okay, then one way to fit models like this, which was already used by Hubbard, is to make perform linearizations. A linearization means to rearrange this equation in such a way that if you plot the data, you should get a straight line. Okay, and this is a linearization from this one, which essentially what it says is that the exponential rate of growth decreases linearly as the scarcity increases, as the cumulative production increases. In the case of Norway, you get this, so it's really quite, it seems that the linear fit is not bad. I repeat, this is the rate of exponential increase in ordinates, and in the abscisses, the cumulative production, which is the indicator of scarcity. And you see that this decreases quite linearly. The data points are not years, they are, at the end, well, at the right they become years, but at the beginning each year has only a small amount of oil produced, so I put together several years in such a way to get a similar amount of oil produced in each case, and in this way the variability gets more regular. Okay, in this way we can estimate the parameters, R and QP, and then we still have another parameter left, which is phi, and we will, but once we know these two parameters, we can perform a different linearization. Well, in fact, it's just using the other equation. Okay, and in this linearization, I wrote here data points and also two lines. The line below, the blue line, is what you would expect from a logistic equation. The other one, the black one, is the fitted line by a simple regression. Okay, from our model, what we should expect is a line that is parallel to the logistic line, but that is in a higher position, like this one, because the distance between the two lines is the initial condition parameter, phi. That, as I said, should be positive, while the logistic considers it to be 0. I also said that it's a parameter of initial conditions is very susceptible to disturbances, so in general, this straight line should not be very good. In fact, you can see here that it has changes, but it keeps in where it gets after the changes. But in this case, the changes are not very strong, so we can work with a parameter for phi too, which is a good approximation in all the during all the time. Then here an interesting point is that, as I said, Hubbard used a different linearization too to fit the logistic, which was this one. But strictly speaking, it only works for the logistic. In our model, it should be a little different. It should not be really be a straight line. And if you compare with Norway data, okay, here you have the black data points are the forecast from the fitted parameters. The white points are the data. And as you see, okay, at the right end, which is what Hubbard would really use, so it's not incorrect to perform a Hubbard linearization, but only works for the right end, where it progressively approaches a straight line. But here you can get a good approximation for the whole trajectory, except a few data points at the beginning that will correspond to the initial investment. So it has some advantages, because it means that you can use more data and that you don't have the danger of some bias remaining at the end of the trajectory. Okay, so as I said, this is and then this is the same in a logarithmic scale. That is useful to show that the fit is well. It's clearer here. And here you have the curve, the reconstructed curve in black and the empirical curve in white. In this case, that is simple. We could even try to make some forecast. Of course, this is always very dangerous because there could be changes. But the forecast here is that the ultimate oil that will be recovered will be this one. And another forecast is that after this year, Norway will not be able to sustain its own current consumption. I know that some of you here got a little different data. In fact, I don't have the interval of variability here. It's just the best guess. Okay, and I think I don't have much time left, so I will run faster now. Okay, this was the easy case, but as I said, you can do some interesting things with this for more complex cases. One of these is that these parameters can be expressed in terms of other parameters that make more physical sense, which are this one, which is the most important number in epidemiology, which is the basic reproductive number, which essentially means for each amount of production that you have, how much production will you get in the future, which means which portion of what you get is going to be reinvested and with which in more production and with which efficiency. And this doesn't tell you when this is going to happen, so that you need another parameter that sets the time scale. For example, here you have another instance with the same reproduction number that takes place in a longer time frame. So for this, you have another parameter. And these are parameters that in principle could be predicted from economic and technological information, perhaps. And then you also add another parameter for the total, which is related to the total oil availability, and these parameters make sense so that if you have changing economic conditions and changing technological conditions, you could model changes in the parameters of this equation that remains close to the logistic while the parameters are constant. Okay, Jean Laherre suggested me to study a more difficult case, like for example, the UK. Of course, this is not a simple curve, but if you perform the linearization, you see something like this. You see that, okay, the series is short, you cannot be very sure of what's going on, but it seems that the linearization is not so bad. And that you have a fluctuation, a kind of symmetric fluctuation here that first goes down and then goes up, which would suggest that this is just a variation in the parameter alpha, which means that there is no change in the basic reproductive number, but just that there is a kind of redistribution of production, some spare capacity that is used later, or some reinvestment that is performed later, but there is a compensation here, and I will show that you find this also in other cases. Well, this is the other linearization. Also, you find that it goes down, but then it recovers. So even in this case, you get the same phi. Here you see that even in this difficult case, you can get quite a good approximation to this figure, which would be linear in the simplest Haber approach of Haber's linearization. And okay, now going faster. Another interesting case, of course, is Saudi Arabia. Interestingly, you also seem to have this kind of redistribution here of this phenomenon that could be interpreted as a change, as a temporary change in alpha. You first get a drop, which is of course the oil crisis, but then there is a fast recovery, and the overall line seems to keep quite similar, suggesting similar parameters. Of course, you also get a trend here. Well, the white spot is the current year production in the optimistic assumption that it will be in the second half of the year, similar to the first half, which we still don't know. Of course, you can fit a straight line here, and we could even dare to do predictions. In principle, this would suggest that Saudi Arabia has already peaked, but don't take this seriously, because we know well, first, that here there is a lot of noise, and second, that we know well that institutional factor is very important in Saudi Arabia. We don't know if the model works here, but we cannot say that it doesn't work. This is the zero line where it would peak. Another interesting case is the Soviet Union, of course. Interestingly, if you perform the first linearization, you find that in the first period, it agrees quite well. So it seems that there was quite the rate of growth of production was declining quite steadily. So it seems that the peak that they reached was quite predictable. You see that after the peak there are some complex reactions, and well, the well-known attempt by Gorbachev of raising the production, they declined it again, then the Soviet Union collapsed, and then you get a strong rise of production again in the new context after the Soviet Union. Of course, As I said, I have still not performed econometric analysis of what's going on with the parameters. That is possible, but this would suggest in principle that here there is a real increase in the basic reproductive number, not just a fluctuation in alpha like before, but a real increase in the basic reproductive number. But well, the other side of this is that if this model works well, okay, an increase in the basic reproductive number also means that the decay that you see here, that the slope of this decay will be steeper after the basic reproductive number will have increased. Okay, this is, I mean, it's still not quantified by how much, but there is something to take into account. That is, if now the basic reproductive number stabilizes, this steep in principle should be stronger. And okay, perhaps after all of these instances, someone expects me to apply this also to the world as a whole, but well, this was just a reminder of the meaning of the parameters. But and this is, okay, we have no time, but this is just a stochastic version of the model, which is a different approach. Instead of trying to find out what happens with the parameters, performing a stochastic approach, which works quite well for the United States. And well, better, but this we don't have much time. So, as I said, I'm not going to apply this method to the world for one reason. If you try to apply it, of course, you can perform this, which should be the linearization, but really, this is not linear. In principle, it seems that there is a first period with height growth rate, then the period of turbulences of the late 70s, early 80s, and so on, and then a period where you cannot, where there are fluctuations, but you cannot see a clear trend in the rate of change of production. Again, the white spot is corresponds to the assumption that during this year the production will stay in the second half like in the first half. And so what this means is that to have good predictions for the world level, you need other kinds of information, like the kind of information that has been mentioned here of specific oil fields, and that will be mentioned in the next presentation, I guess. And so with all of this discussion about the specific shape of the curves, I'm not pretending at all to replace these other methods, which at the end are better because they use more information, but just to propose some mathematical tricks that perhaps could be useful for the next round of predictions that you who really know about this are going to perform. And well, that's it. I leave you with the bacteria, which is stuff for thought. And I don't know if there is time for questions.
Okay, thank you very much. I see that your model does not predict the end of the world, but the end of the bacteria, which may be better.
Yes.
So we have time for a few questions.
I was just wondering, you dare to take this equation and fit it to a number of countries, and I still don't really understand why you don't dare to do that for the world. Because to me it seems like you're trying to fit a mathematical equation to some observations, which is fine. I just don't understand why you don't dare to do that at the world scale.
Okay, simply because in this case, which was the simple, I mean, the fit is not just to find the estimation for the parameters, but also to check if the model works well. In this case, the trend looks quite linear, so it seems safe to apply it. In this case, you don't know for certain, but it's consistent with a linear trend. In this case, the same. You don't know for certain, but it's consistent with a linear trend. In this case, at the beginning, it was clearly consistent. After it was no longer. Here, there were clear disturbances. But here, if you look in detail, it doesn't seem to have a linear trend. I mean, because in the middle there are clearly the oil crises that we know that were produced because of political turmoil, so which is something that deserves consideration apparent. Really, it's displayed by a higher variance. And if you take after this, you cannot see a clear trend. No? So there could be indeed an underlying trend that they are trying to correct with OPEC price policies and anything. But I don't think that it's really safe to apply the model because I don't see clear evidence that there is the linear trend here. No? I mean, it could be the linear trend behind here. Well, if you apply, I can say that if you apply the regression, which I have done, of course, you find that the oil has already peaked. But only from this, only from the production data, I would not dare because I see here a different shape that is not linear. It's this.
Okay, I remember from when I was at college, well, and from the graphs you've shown, the curves that you get with these equations, they aren't symmetrical, right? So my question is, generally speaking, is the decline faster or is it slower or does it depend on the parameters?
In this case, as you see, the only change from the logistic equation, which is symmetric, is the addition of this other, well, doesn't matter, of the parameter phi that corresponds to initial conditions. As I said, usually it should be positive, which means that there is a slight asymmetry, that there is some asymmetry, but in the opposite sense, in this case, that the way down is a little slower than the way up. On the other hand, okay, about symmetry, there are some other things to say. First, that the fact of introducing here the effect of scarcity as a linear term, it's because, well, it's because of the same reason that was originally introduced in, or justified in an ecological context by Lotka in the case of the logistic, which is because it's the simplest case using, well, for who knows about this, using Taylor series expansion is the simplest. Well, it's the biseable model to use, and but in theory you could get more complexity and you could deal with it introducing asymmetries. In this case, with the data analyzed, there is not still clear evidence of an asymmetry, but potentially could exist. But well, it seems using this data that the linear approach is good enough. No? And well, but then still another point is that. Well, here, in the last speech we were speaking about multiple feedbacks and so on. This is essentially an oil model assuming that the parameters of production, that the underlying parameters of production are quite constant, but of course this is not necessarily true, but well, probably it is not true. It can be true in specific areas, probably for Norway it can be true, for the United States it can be true because they are just embedded in a largest market. For the Soviet Union it probably was not true. I mean, there is some ongoing discussion of whether peak oil contributed to the collapse of the Soviet Union, and in this case there were clearly strong political economic feedbacks that in principle if you can model them you can introduce into the model because of this physical meaning of the parameters. And in the world as a whole, of course, there will be very strong feedbacks that could perfectly produce a collapse, or I don't know. You are modeling this other part.
Hello, I was just going to say, I think you would have to make a distinction between those countries that work like we would have it with bacteria, where the energy that is suddenly found is made available at an increasing scale, which is in the US. That's why Hubert also predicted the peak so well in the US, because it was a free market and there were no decisions on a political level. Whereas there's other places where, like in the USSR, where there were political decisions of how much oil really to put on the market. Same with OPEC, obviously.
In this case, it would seem that the political decision also was some kind of maximization, because until the point of the collapse, you don't see here a signal of a different behavior, that just the declining trend. So in this case, it seems that they also tried to maximize or to keep a little, well, that they didn't behave so differently. But I agree completely that potentially, well, of course, that the difference between bacteria or viruses and ourselves is that in principle, we should be able to get awareness of what is going on and to redirect what is going on, which is, I think, is the usefulness of ASPO. But well, and until now, it doesn't seem that we are doing very different from bacteria, but I hope we can do. Well, of course, there were other kinds of interferences, OPEC, and so on. This is why I'm not any sure of fitting this model to the whole world, but I hope we are able to introduce a different interference in the model, which is the awareness and solidarity and so on interference.
Thanking all the speakers, and be back here around 11:45. Thank you.